The next person who will be speaking is Linda Hicke. Dr. Hicke joined the University of Texas staff as Dean in July of 2012. She holds the Robert Boyer Chair in Natural Sciences, and prior to her appointment at UT, she was at Northwestern University, where among many things, she also served as director of the Center for Cell and Developmental Biology. Linda is a recognized expert in cell biology. She received her PhD in biochemistry from the University of California at Berkeley, and 2 postdoctorals, one at the University of Cal San Francisco and one at the University of Basel in Switzerland. Linda wears many hats. I could tell you all of the things that she's published and all of the degrees that she has, but I think it's nice to know that among the hats that she wears is that of an educator who is committed to promoting excellence in research and education in the natural sciences. She's also a dean, and as all the other deans know, that takes a balancing act of many things, trying to keep the staff happy, trying to keep faculty happy, balancing budgets, working with department heads, advocating on behalf of undergraduate education, trying to get more money for the school, and at the same time trying to attract the best and the brightest graduate students and faculty for the graduate students. She's a mother, she's a wife, but perhaps more importantly for me, she's a visionary. And after she came to the University of Texas, she quickly established a task force to do a 5-year visionary plan and to lead the university in a strategic plan where 3 of the most important things are to develop scientific leaders, to promote discovery, and to create impact. For me, Linda is just a warm and caring and engaging person that I'm pleased to call my friend and have pleased to work with for the last couple of years. And so I give you Linda Hicke, Dean of the College of Natural Sciences.
So thank you, Glenn, for that very kind introduction. Thank you all for being here today. It's great to be back in Midland. I was here about a year ago and met many of you who are in this room. As Glenn said, I am the Dean of the College of Natural Sciences. We're now the largest college at UT. We have about 11,400 undergraduates enrolled this year. One of the reasons that I moved here from Northwestern University in the Chicago area about 2 years ago, which was kind of a tough time, you know, we've been going through some tough times here in Texas, was that as Senator Salinger referred to, this was clearly a place where there was incredible support for higher education. People were thinking clearly and passionately about where we were going to be going in higher education. The dedication of the faculty here to undergraduate education and the role of innovative programs in STEM education and education, as Dr. Pennybaker has talked about, was just phenomenal. Coming from a relatively small elite private college, the things that were happening at the University of Texas were impressive beyond belief. And so I decided to come here and join you. We visited here in Midland about a year ago, and we talked when we were here about one of the programs in the College of Natural Sciences, which I think really represents something that is unique, that is done at a very large scale. And importantly, I think now for us at this time, is a demonstration of how integrated the research and the education missions are of a university like the University of Texas. This program is called the Freshman Research Initiative. It is a program in which groups of 15 to 30 freshman students come in and they work on a completely novel, independent research project that it has been designed by a faculty member in the natural sciences. Those of you who know Bloom's taxonomy, the first level of really getting students to engage in learning very effectively is to explore. And when these students come in as freshmen and they work on a completely new research project that is the very heart and passion of a faculty member, they have that opportunity to explore and ask questions and learn how to solve them before they have to learn all the content and the facts and things. And that triggers their desire to learn. The statistics and analysis from this program have shown that it increases retention of students in our undergraduate education programs, particularly those from disadvantaged communities. So the number of Hispanic students that remain and receive a degree in the natural sciences is twice that, who have participated in the freshman research program is twice that of students in control groups. So it's a very effective program. Now about a third of our freshman class, 850 students, are participating in it, and it is one of the examples of things that are happening at the university that is really world-changing, I think. So I'm very happy to be here celebrating this first UT in Midland event. I think it's a wonderful collaboration between our colleges that we can all come here together and hear each other talk. I've heard fascinating talks this morning. We're going to hear from 3 more outstanding faculty this afternoon. And before I introduce our speaker from the College of Natural Sciences, I just want to recognize and talk a little bit about the exciting updates that are happening at our Western Outpost McDonald Observatory here in West Texas. I know many members of the Midland community have been involved and supportive of this. The Hobby Eberly telescope is undergoing a renovation, a major scale renovation right now that's going to allow significant experimentation into the questions of what dark energy is. And also, on top of that, we have now participated, the University of Texas will now participate in a once-in-a-lifetime astronomy project in building the giant Magellan telescope that's going to be located down in the Andes in Chile. And this is going to be the next generation of large telescopes. It's going to be 25 meters wide. The mirrors will be that wide. They'll have about 100 times the collecting sensitivity and area of the Hubble Space Telescope. And this is an opportunity to make the University of Texas proud that we can participate in this next project, which I think also is a project that will capture the minds, the imagination of our young scientists to be in Texas and the nation, and get them thinking broadly about scientific questions of galactic proportions. So the other thing I think you'll be pleased to know is that there's been an effort underway with local leadership to partner with the McDonald Observatory in Fort Davis on the growing issue of oil field lighting as it affects the ability to observe in the night sky. These efforts are going to have just a lasting impact on our ability to continue to do great astronomy and understand our universe. And I want to offer special thanks to Bill Dingus and Richard Masterson, and from Concho Energy, Tim Leach and Scott Kidwell, for their fantastic efforts in working on this project, which is really critical to our kind of crown jewel, the McDonald Observatory, and its ability to continue to contribute significantly to astronomy. So speaking of astronomy, it's now my pleasure to introduce Steve Finkelstein. Steve is an assistant professor in the Department of Astronomy in the College of Natural Sciences. He received his bachelor's degree in physics and astronomy from the University of Washington and his PhD in physics from Arizona State University. He was a postdoc at Texas A&M, but he's figured out the light and has moved over to UT, bringing with him a very prestigious Hubble Fellowship. He's going to be talking to us today about the focus of his research, and the title of his talk is Searching for the Most Distant Galaxies in the Universe. And Steve is one of our researchers that in the past year has made one of the most significant scientific discoveries published in the journal Nature coming out of the college. And his research primarily involves images from the Hubble Space Telescope and some of the largest ground-based observatories in the world. And we are going to be part of the next generation of those largest ground-based observatories with the giant Magellan telescope. So we are incredibly proud to have been able to recruit Steve to the University of Texas, and please welcome Steve as our next speaker today.
Thank you, Dean Hicke. It's a great pleasure to be here to share my research with all of you. We heard some very interesting talks this morning, and I hope that I can stimulate you guys in a very different but very equal way as we together explore the mysteries of the universe. So As Linda said, I look for the most distant galaxies in the universe, and I'll kind of motivate why I do that throughout this talk. But really, what I am, and when you go home tonight and you talk to your families, your friends, I want you to tell them that you met a real live time traveler. When we look at these images, we are literally, well, not literally, figuratively traveling through time, right? We don't build time machines, but we do in a sense because when we build telescopes. When we look at things out in the universe, because light travels at a certain speed, it doesn't get to us instantaneously, it travels at the speed of light. We see things as they were a little bit into the past, if they're close by. The sun, you go out and look at the sun, if it's clear outside, don't look directly at it, of course. But you're not seeing it as it is right now, you're seeing it as it was 8 minutes ago, because it takes light from the sun 8 minutes to get to us here on Earth. All right? The sun doesn't change that much on 8-minute time scale, so it looks pretty much the same. But if we go look at the nearest large galaxy to our own, the Andromeda Galaxy, and I'll show you a picture of it in a little bit, we're not seeing it as it is today, or even 8 minutes ago. We're seeing it as it was 2.5 million years ago, way back into the past. As it turns out, even galaxies don't change on 2 million year timescales. And so Andromeda looks broadly the same right now as it does when we see it, although maybe some of the biggest stars have exploded in these enormous events called supernovae and are no longer there. But if we really want to figure out how the universe formed, how it evolved, how we formed our beautiful complex Milky Way, we need to look even further back into the past. And for that, we need big state-of-the-art observatories, and we need to image the universe very, very deeply so we can look very, very far away. So the image here that is slowly showing up is the Hubble Ultra Deep Field. Actually, raise your hand if you've seen this image before, the Hubble Ultra Deep Field. It's become one of the most iconic images to come out of Hubble over the past decade. This is what happens if you take an observatory, you put it into space, and you stare at one region of the sky for 100 hours. There's about 5,000 galaxies in this image. You can't see them all. Some of them are tiny little specks. There are about 5,000 galaxies. This region is the size, if you take a hair from your head and hold it out at arm's length, that's the width of this image. Tiny, tiny corner of the sky, and it's filled with galaxies. This was actually an enormous risk for the Hubble Space Telescope. They kind of received a lot of backlash before they got these images because they didn't know what they were going to see. And some people thought it was a colossal waste of time to stare at a region where they thought there was nothing. But it turns out it's filled with galaxies. Some of these galaxies are billions or even 10 billion, tens of billions of light years away. And so we're looking very far back into the past. So before we get into exactly what I do, we should take a step back and just define what is a galaxy. So we live in a galaxy. We live in the Milky Way galaxy. That's the name we've given to our collection of stars. It's a gravitationally bound collection of stars. So we all kind of orbit the merry-go-round around the center of our galaxy. It takes our sun about 220 million years to complete one orbit around the center of our galaxy. Back in the 1920s, we really didn't know if there were other galaxies. We had looked out into the sky with our telescopes at the time and saw these little faint diffuse clouds that kind of look spiral in structure. And they were called these spiral nebulae. And there was a huge debate at the time about whether they were regions within our own galaxy or different island universes, as they called them at the time. And there was a big, wide open, and excellent debate, and it was proof what evidence was shown. We figured out that these were, in fact, independent systems, very, very far away, much further than the extent of our own galaxy. So this is the Andromeda Galaxy I mentioned. This is our neighbor, about 2.5 million light years away. We cannot take a picture like this of our own galaxy because we live inside of it. But we can map the stars in our galaxy very well, and we think that we look pretty similar to this. This is a spiral galaxy. You can see it's kind of yellowish in the center, which tells us a lot. It tells us there's some old stars there, and it's blue on the outside. It tells us it's forming lots of new stars on the outside of this galaxy. But not all galaxies look like this. We look around our local universe, and we see there's a wide range of galaxies. This is a galaxy called the Sombrero Galaxy. It looks like a sombrero, right? We're not always creative with names. I will tell you later the name of our most distant galaxy, and it's not very inspiring. And we actually tried to come up with a better one. So this is the Sombrero Galaxy. This is something probably like Andromeda, but we're looking edge on. And you see this dark band there. That's actually little bits of dust in the galaxy blocking the light. And dust becomes very important. We'll talk about that in a little bit. But there are other galaxies. This is an elliptical galaxy. Those rings there are some sort of artifact of the projection system. But elliptical galaxies are basically big yellow spheres of stars. They look very different from Andromeda. And when we study these galaxies, we realize that elliptical galaxies are not forming stars anymore. Spiral galaxies like Andromeda or the Milky Way are still churning out new stars every year. And then there are a lot of examples I'll show you. I'll only show you a couple more. This is M82. This is a galaxy that has an extreme starburst at its center. It's churning out a lot of stars, such that the energetics from the stars when they blow up are kicking tons of gas and material out of the galaxy. And that's what these red regions are here. These are huge outflows. It's kicking stuff out of the galaxy. It's incredibly energetic. And there are also these types of things called galaxy mergers, where two galaxies actually come together and collide. And we think that's actually how you form those elliptical galaxies. These galaxies come together and collide, they make a big starburst, like is shown in M82, and they kick all the rest of the gas out, and then they can't make any more stars, and they turn into these elliptical galaxies. So this is what things look like in the nearby universe. When we try and look back in time, very far back in time, billions of years back in time, and we look in the distant universe, things look very different. All right, so here's the Hubble Ultra Deep Field again. We can actually see some spiral galaxies. This one's probably nearby. Here's an elliptical galaxy. This one's nearby. This is actually a star in our own galaxy that's just away. But there are all these tiny little specks in the background. I can tell you where the stars are. There's 3, I think 2 shown in this image, 1 here. All these tiny little specks, those are really distant universe galaxies. And they're tiny little clumps, tiny little train wrecks. They look nothing like the Milky Way today. And so the name of the game, the goal of my research, is to figure out how you go from a universe filled with these to a universe filled with these. And we've got about 13.5 billion years with which to do this. The age of the universe is about 13.8 billion years. And so it's kind of a relatively short period of time because things take time to happen. It takes billions of years for galaxies to collide and things to happen. So it's a very interesting process. So we have a decent idea of how this works thanks to dark matter. And I won't get into dark matter much in the talk, but I'll be happy to take questions about it afterward. This is a movie of what happens if you make a simulation on your computer, throw a bunch of dark matter particles in, and just let it go. And you can see, you'll actually start it over. It starts out very sort of diffuse and homogeneous, and then things tend to gravitate together. That's exactly what's happening. Dark matter only interacts gravitationally. It does not interact with light. That's why it's dark. We can't see it. But we understand gravity very well. And so if you throw a bunch of dark matter particles into a box on your computer and just press play, this is what you get. And this matches very well what we see in the universe. These bright regions, those are big clumps of dark matter. These are the sites of galaxies, of galaxy formation. So when we go and look out into the universe, we are seeing kind of these beacons in the dark, these shining lights of galaxies from the intersections of these dark matter filaments. We can't see the dark matter, and we can't even see the faint little bits. We tend to see the brightest bits from that. But it gives us kind of an idea of what we want to go look at. To do this, we really require cutting-edge facilities. Astronomy, in particular, the very distant universe astronomy, is sort of in a revolution due to this cutting-edge facility, the Hubble Space Telescope. Now, you may be aware, Hubble launched in 1990. It's not exactly brand new, it's 24 years old. But what you might not know is that Hubble has become a new telescope several times. 5 times during its lifetime, we have sent the space shuttle up with astronauts who risked their lives to go and repair things that are broken, add new instruments, add new capabilities. And the last time this happened, and it actually will be the last time because the space shuttle has been retired, was in 2009. And the astronauts went up and they actually repaired a number of things, and they also installed a brand new camera that sees into the near infrared. And the near infrared, this is just redder than our eyes can see. This is actually quite important for studying galaxies in the distant universe. We need this capability to do it, and we can't do it very well on Earth. If your eyes could see at near infrared wavelengths, the night sky would appear to glow. There are molecules in the atmosphere that are glowing at near infrared wavelengths, and it makes it very difficult to see those faint little galaxies. And so we need to go to space to find them, and for that we have this fabulous facility, the Hubble Space Telescope. So we need to talk to Hubble a little bit more to see why we need to look at the near infrared, but we need to talk to Hubble the person. So this is Edwin Hubble. He was an astronomer. He is, of course, who the Hubble Space Telescope was named after, but he's famous for a few other things. First of all, those different galaxy shapes I showed you, he classified those. It's known as the Hubble sequence, or the Hubble classification of galaxies. But he made another very important contribution. He was doing a survey of galaxies, and he was measuring how far away the galaxies were, and he was measuring how quickly they were moving, whether they were moving towards us or away from us. And when he plotted these against each other, he found a correlation, which is one of the most exciting things you can find in science, because it means something's going on, and then it's up to you, or you and your colleagues, or you and the world, to try and figure out what that is. So he plotted this correlation, and this is what he saw here. This horizontal axis here is the distance to a galaxy, and this vertical axis here is the velocity to a galaxy. And each of these little points are different galaxies, and he didn't have a computer at the time, so he probably took a ruler and just drew a line through them. And this is known as Hubble's Law. It says the more distant a galaxy is from us, the faster it's moving. Right? So number one, all galaxies are moving away from us. And number two, the more distant ones are moving quicker. And so this tells us we live in a universe that is expanding with time. It appears to us as if we are at the center of this universe because everything's moving away from us. But if you hop on over to another galaxy a few billions of light years away, it will appear to them as if the universe is expanding away from them as well. Everything is moving away from each other. All right. So how does this affect our observations? This is actually excellent for us because of something called the Doppler effect. You're probably most familiar with the Doppler effect if you've ever been on the road when a train has come by. You hear the train whistle. The train is approaching you. The whistle appears to go up in pitch to your ear, and then once the train passes you, the pitch goes down. And that's because the sound waves are getting compressed as the train is coming towards you from your point of view, and once the train passes you, the sound waves get stretched out, and stretched out sound waves appear lower in pitch. So the same thing happens to light, as shown by this very crude graphic here. If you take a light source, if I turned on a flashlight and I ran at you at an appreciable fraction of the speed of light, which I cannot do, that flashlight would actually start to appear bluer because the light waves are getting compressed, and compressed light waves look blue. All right? That's not what's happening in the universe. Everything's moving away from us. So if we took that same flashlight and I ran away from you really quickly, those light waves would appear stretched, and that flashlight would look redder than it does. So we come back to Hubble's law and we see, okay, everything's moving away from us. When things move away from you, they appear redder. That means that everything should appear redder than it does. Okay? But it means the more distant galaxies should appear even more redder than the closer galaxies. So if we have a decent idea of what a galaxy should look like, all we need to do is go out there, measure how red it appears, and we can figure out how far away it is, which is great. Measuring the distances to things is one of the most difficult things to do in astronomy, and people have been struggling with that for centuries. Right? But now that we understand the expanding universe very well, if we understand this expansion rate, which we do, and which HEDTEX will help clarify, we can simply go out, see how red things appear, and then that tells us how far away they are. All right? So I mentioned the near infrared. The galaxies in the distant universe are moving so fast away from us that all of their visual light that you can see with your eyes, or even the ultraviolet light, bluer than your eyes can see, that's all shifted, redshifted into the infrared, into the near infrared. So we need these new technologies, these new capabilities to be able to see these galaxies. These galaxies that I'm going to show you, they are literally invisible. You cannot see them in visible light because they are moving so quickly away from us. So just to give you a baseline, astronomers, we term this redshift. Redshift is basically equivalent to distance. And we just give it a number, and I'll try not to, but I'll probably spit out a few of these numbers as we go along. We live today at redshift 0. We are not redshifted to us, of course. And this second column here shows time since the Big Bang in billions of years. So we now live at a time 13.8 billion years from the Big Bang. In this talk, I'll show you some distant galaxies we've been looking at a redshift of 7.5, which corresponds to a time only 700 million years after the Big Bang. And we can find galaxies at all redshifts, all distances in between. So because we look back in time, we get snapshots of what the universe looks like at each of these distances, which is a snapshot at each of these times, and we literally can make a movie of it and see how galaxies evolve with time. And that's the basis of our research. All right, so I'm going to have you guys all put on your time traveler hats now, and we're all going to travel through time together. This is that same image, that Hubble Ultra Deep Field, and we're going to explore a few galaxies, and you're going to try and figure out what's going on. You're going to be galaxy evolutionists, as it were. So we zoomed in very quickly. Here's a galaxy. It looks like a spiral galaxy. It kind of looks like Andromeda, or the Milky Way. But we're seeing it as it was 8.5 billion years after the Big Bang, or about 5 billion years ago. At a redshift, Z stands for redshift, of 0.5. And what we see is, okay, we step back 5 billion years in time, an appreciable fraction of the history of the universe, and we still see spiral galaxies. We can actually still see elliptical galaxies. We still see, as we say in astronomy, the Hubble sequence. Galaxies look like they do today. So if we want to figure out how the Milky Way formed, we need to go much further back in time. And so we'll pan around this image again, and we'll take a step out to a redshift of 4, now getting into what we call high redshift astronomy. And here's a little clump here. Okay, these are the clumps and train wrecks I'm talking about. When you go out to the distant universe, all galaxies look like this. They look nothing like the Milky Way. All right, so now we're looking over 12 billion years into the past, only 1.5 billion years from the Big Bang. All right, and you notice this galaxy kind of looks a little bit red. I should say that redshifting effect, the expansion of the universe making everything red, we've actually taken that out of this movie. We can combine the filters in a way so that we are seeing this galaxy as it would look if we were right next to it. All right, so it's red, and that's important, but we'll get to that in a second. We'll take one more step back to a redshift of 6. And around a little bit slowly. Time travel is hard work. All right, zoom in. Here we go. Okay, we jumped back about 600 million years from our last step, right? Now at a redshift of 6, this galaxy, this thing right here, what color does that appear? Blue. It appears blue, right? Broadly speaking, when we look at galaxies in the distant universe, we see that they transition from being red to blue. And this is very important. So this is the basis of a paper that I led in 2012. This is an image, actually a different region of the sky, a survey I was a part of that was the largest survey in the history of the Hubble Space Telescope. Each of those circles around the image is a distant galaxy. And what we tried to do is we tried to see what color the galaxy was as a function of its distance from us, from the Earth. And we made this plot here. This is a real plot from our paper. This axis here is redshift, or distance. So the nearby galaxies are here, and the more distant galaxies are over here. And then this is color, where red is at the top and blue is at the bottom. All right, that red galaxy we looked at was here, and the bluer galaxy we looked at was over here. And what we're seeing is only over a very short period of cosmic time, less than 1 billion years, galaxies go from being blue to red. All right, that may seem like it doesn't matter, but it's actually incredibly important because we know what makes galaxies really red, and what makes galaxies red is dust. This is not the dust that you find, under your cabinets or under your bed or whatever. These are actually more closer to soot from like a fire. Dust are tiny grains of carbon, magnesium, silicon. These materials did not exist at the Big Bang. After the Big Bang, the beginning of the universe, there was only hydrogen and helium. All of the heavier elements, those were formed in the cores of stars during the process of fusion. Okay? So we are literally tracking the buildup of these heavy elements in the universe, but more importantly, these dust grains, these are the things that stick together to form bigger and bigger rocks and eventually form planets. And so this is literally looking at the buildup of planet-making material early on in the universe. Very early on, less than 1 billion years after the Big Bang, there was none of this material there. You could not have planets. Only a short time later, a few 100 million years later, you built up a lot of this material, and you could start to make planets. All right, so I've skipped over something very crucial. If you were an audience of astronomers, you would be yelling at me by now, because I told you that we can tell the distances to these galaxies by how red they look. And that is true, but it's approximate. We would really like to measure very precise distances and be sure that we're looking at things that are red because they're very distant versus things that are red just because they have a lot of dust that have to be close by. So to do this, we need to turn to a technique called spectroscopy. Spectroscopy is what happens if you take light and you disperse it into its component colors, shown here with a prism. You can see a nice rainbow of light here. But spectroscopy is fantastic because there are hidden signals in the spectra of stars and galaxies. It tells you about the chemical elements that are there. On the bottom, I give you an example of something called an absorption line spectra, and you can see hydrogen absorbs light at a very specific point, a very specific wavelength. Calcium absorbs light at a specific wavelength over here. So if you see these lines, you say, aha, I know there's hydrogen there, which is easy because there's hydrogen everywhere, but you say, oh, I know there's calcium there, or I know there's iron there. Even more importantly, we know where these little dips in that spectrum should be, and when these galaxies get redshifted, the wavelengths or the position of those dips move. But if you find them, you know very precisely how redshifted that galaxy is. All right, so I told you all this, we actually can't do this in the distant universe. The galaxies are too faint. But luckily for us, they are forming stars very rapidly, and that causes the gas to glow and creates a different kind of signature known as an emission line. So this figure here is basically the fingerprint of our galaxies. These little dips here, those are absorption lines telling you about different elements. But you see this big spike here? This is an emission line from the hydrogen atom. Hydrogen is everywhere. And so if we can see this line, we can tell exactly how far away these galaxies are. And this is what we want to go to. To do this, this is where the large ground-based telescopes come in. The Hubble is fantastic, but it's only a 2.4 meter mirror. It's the size of your average NBA player. The more mirror we have, the more glass we have. Maybe not your average, your tallest NBA player, certainly taller than me, but the size of the cube. All right. Telescopes are basically big light buckets. These galaxies are so far away, we're getting so few photons from them, we need bigger buckets, we need bigger mirrors to get more photons. That's why eventually we need a giant Magellan telescope to do this. Right now, the state of the art is the Keck Observatory on top of Mauna Kea in Hawaii. There are actually 2 telescopes here. It's very horrible to have to go to Hawaii for work. I tell you, we complain all the time. And we don't even work from the top of the mountain because the air is so thin. We actually work down at 1,000 feet across the street from a Starbucks. It's horrible. And I'll show you a picture here. This is actually the control room. I went there with my team in April of last year. There's myself. This is Mimi Song. She's a graduate student at the University of Texas who is now leading a lot of this work. And Bethal Tilby for the Aggies in the room. He's a postdoctoral researcher at Texas A&M. And we're sitting in the control room here. Over on the left, this is actually our video chat with the telescope operator who is up at the top of the mountain. So we do talk to people on top of the mountain. So we need these big telescopes because we need to look at these faint galaxies, and they get even fainter once you disperse the light. So we have to do this from the ground. And so we went there in April of 2013, and we measured the distance to this galaxy. This is an image where we did not remove that redshifting effect. You can see how incredibly red this galaxy is. We took a spectrum of this galaxy. Remember the one I showed you before with the great peak, and you can tell right where it is? This is what our spectrum looks like. We term it a spectrum only a mother can love. This spike here, there's lots of spikes. They're all junk. They're all noise. But this one right here with the red line conveniently drawn through it, that is that feature. That is this. But instead of seeing all this detail, because these galaxies are so faint, we're just seeing the tip of the iceberg of that spectrum. And that's because we're limited by the size of our telescopes. We need bigger telescopes to see more and to see more galaxies. But what was incredibly exciting about this galaxy, two things. Number one, that distance made it the most distant galaxy ever discovered that we found last year. And number two, it was forming stars at an incredible rate. The Milky Way forms 1 or 2 new stars per year. It's kind of typical nowadays in the universe. If you go back to these distances, most galaxies form maybe 10, maybe 20 stars per year. This galaxy forms 300 stars per year. And now we know the distance to it. We know exactly that star formation rate very precisely. And if I go and talk to my theorist colleagues, the simulators who run models on their computers, they don't see anything like this. And I get to tell them, hey, you're wrong, because I found it. It's out there in the universe. We need to talk and fix your model so that you can make at least one of these galaxies. And it turns out they're not all that rare. What was also exciting, it actually surprised me, so we have a great press department at the Magellan Observatory. We put out a press release that got picked up worldwide. We got a ton of press. This was in October of last year. 150 million people read an article about this on the internet, which is absolutely staggering. We did interviews on CNN, and it was a lot of fun because, especially in astronomy, we're very much taxpayer funded. Our research grants come from taxpayers, and we very much enjoy giving back and talking to people about what we do. So I'd just like to end talking a little bit about the future. As I said, astronomy it's both people-driven, but also technologically driven. And so the future in space is going to be a telescope known as the James Webb Space Telescope. This is a movie similar to what I showed you at the beginning, and I mentioned these bright things. That brightest thing, that's about all we can see now with the Hubble. But we predict there are literally thousands or millions of these fainter galaxies surrounding this bright thing. We would like to go observe them, see what they're like. Do they have metals? What's going on in those galaxies? And for that, again, we need a bigger mirror. So this is what the James Webb Space Telescope looks like. It's being built by NASA. It will actually be tested, the mirror assembly will be tested at Houston either in 2015 or 2016. It's the only room big enough to fit the mirror, Chamber A. They actually have had to refurbish it because it was a historical site. And this will launch in 2018. And it's going to do absolute wonders for studying galaxies in the distant universe, but also for looking for Earth-like planets around other stars nearby, studying how star formation proceeds in our own galaxy. It will benefit every single astronomer, and by definition, as we get back to the community, benefit our entire knowledge of the universe. So just to give you a glimpse of what we'll see here again, you can tell I love this image, the Hubble Ultraviolet Field. I think I show it every day in my class, even though I only talk about galaxies the last month or so. All right. There's lots of galaxies, right? But there's lots of blank space here. We can simulate what we'll see with the James Webb Space Telescope. And this is what we see. Actually, it looks a little bit more impressive on the laptop screen. But there are tiny little faint dots everywhere. Those are those little faint things in those movies. We will be able to go out and see those, identify them, measure the distances, see what their chemical abundances are, and literally trace the formation of our Milky Way. But if we want to learn more about those galaxies, we need large ground-based observatories. The Keck telescope I showed you, where we've been going, this is the workhorse follow-up machine for galaxies discovered with the Hubble Space Telescope. For the James Webb, that facility is going to be the giant Magellan telescope, which is shown here. As Dean Hicke mentioned, we are now a founding partner of this observatory. Our goal is to have about 10% of the observing time, which means that astronomers at the University of Texas will be able to use this telescope about 32 nights or so per year. The diameter, so you notice there are 7 mirrors here. The diameter of each mirror is 8 meters. So each mirror there is almost as big as the largest telescope today. And end to end, it's about 25 meters. And so it does have literally about 100 times the light gathering power of the Hubble Space Telescope. And so I mentioned seeing only the tip of the iceberg for that galaxy, and that's one of the brightest galaxies in the distant universe. We're going to be able to now see the whole iceberg, not just for one galaxy, but for several galaxies. And we will have access to this again at the University of Texas. And so just to end with what makes all this fantastic research possible, and I wish I had more time to talk about all the great research that's being done at the University of Texas, including one of the most exciting things going on in astronomy today, which is finding planets around other stars. We now know of thousands of planets around other stars. Many of them have been confirmed with the Hubble telescope in West Texas. But what makes this possible, again, is people and facilities. At the University of Texas, we're able to recruit and retain world-class undergraduates, graduate students, and faculty. We regularly compete. I've been doing graduate admissions, and we're regularly competing with schools like Princeton and Caltech for the top graduate students, and they do come to the University of Texas. And the reason why they do that is because we do have excellent faculty. The reason why we have excellent faculty is because we have excellent facilities, and we always have an eye forward to the next great facility. So the Hubble telescope has been great, and we're making it greater with this refurbishment, this upgrade and CATEX project that we'll be doing. And then we are now, as I said, going to be involved in this giant Magellan telescope. And because we're involved at such an early stage, we are going to be leaders in this next generation project, and that will allow us to recruit and retain these excellent students and excellent faculty from now many decades into the future. Thank you very much. I think I still have time for questions. I know I was ignoring your warnings back there. Sorry.
Go ahead.
Oh, yeah.
How did you get interested in astronomy?
How did I get interested in astronomy? So you did ask me this question last night and said I should tell the story, and I forgot. If you ask a lot of astronomers that, you actually get the kind of classic story. I was out in the backyard and I looked through a telescope and I was drawn by the wonder of the stars. I grew up in Seattle. All the rumors you hear about Seattle are true. It's cloudy a lot. So we did have a telescope, and I did see the stars, but I wasn't really inspired to pursue a career in the sciences until I was in high school, and it was specifically my high school physics teacher, Tom Happ at Issaquah High School. He's still there in Issaquah, the suburb of Seattle. He was excellent in every way, and it really gives me a great example of how an excellent educator can literally change the course of future people. I don't really know what I was going to do in college at that point until I took this course in my junior year of high school. I was actually able to go back to my high school this December when I went home. I worked with Mr. Haff, as I still call him, he gets mad at me. I worked with him to set up an assembly for students interested in the science at school, and I was able to go back and tell this story to him in front of all the students and all the staff there, and it was a really great experience. Yeah. Yes?
Did the technology already exist to build these huge mirrors, or has it had to be created? And if it did exist, what was it already being used for? And if it didn't, what are some of the other capabilities that it will be able to provide?
Yeah, that's a great question. So the James Webb Space Telescope specifically, we just had a great lecture on this last year at UT by one of the deputy project scientists. And I won't even remember them all, but he listed 7 key technologies for the Webb that did not exist that they had to invent. One of them was the mirrors. The mirrors are actually made out of beryllium because they're more reflective in the near infrared where this telescope will work. And they had to go mine them, I think, in Utah and develop the capabilities for these mirrors. And I wish I had remembered, he actually had some very specific industry applications of various techniques of the Webb. So they do happen from this telescope. The Giant Magellan telescope, we build 8-meter mirrors today, but we built one of them and we put them right in the middle. The interesting thing about the GMT is that we want all of those mirrors to work together. And so each mirror has a different and a very specific shape. And we actually didn't know if we'd be able to do that. And so these mirrors are built under the football stadium at the University of Arizona in the Stewart Observatory Mirror Lab. And I think it was kind of a relief once they finished the first mirror and saw they could actually build it to spec. And so absolutely, every time we're building a new telescope, we're always pushing the limits of technology. If we could have done it, we would have done it already. Yes?
What about life in space? Is there other life out there?
Is there other life out there? This is a great question because I can say I don't know. We don't know. I certainly believe there is. There are over 100 billion stars. 100 billion, think about the number. 100 billion stars in our galaxy. And if you take the Hubble Ultra Deep Field image and it's about 5,000 galaxies there and multiply by the number of times you could tile that around the sky, you would come up with hundreds of billions of galaxies. And that's the ones we can see. The ones we'll see with the Webb, there will be even more. And so seems to me there are unlimited possibilities. And the fact that we haven't found any yet, I think it's simply because we haven't been around that long. Yes?
So I heard Cosmos.
Yeah. Cosmos is excellent, by the way. Astronomy as a whole, thank all of you for watching that, and thank Neil for putting that on.
He suggested that there's a view that there may be many other universes.
Mhm.
What's the basis for that?
The basis for that is, oh, sorry, yes. Are there other universes, or why might we think there are other universes? We still don't know what caused the Big Bang. And there's a period very early on in the history of the universe known as inflation, which actually got a lot of press because we think we have empirical evidence for it. So something caused the beginning of the universe, the Big Bang. We don't know what that is. Right after that, a tiny, tiny fraction of a second after that, the universe increased its size by a factor of 10 to the 30. So it's a 1 followed by 30 zeros over a tiny fraction of a second. All right, and that made our universe today. And then it continued to expand much, much more slowly. We don't know if that only happened once or if that happened several times, if there were little inflated bubbles around, such that we could not communicate ever with any of those bubbles. And you could basically consider those different universes. So I know there are physicists that study this, and I'm sure that they believe that maybe some way we will have a way of actually testing and seeing whether those are real, but that's a little bit hard to see. But it certainly is an interesting thought experiment. And it's certainly possible because, again, we don't know what caused the Big Bang. We don't know what caused this inflation process, although we do know that they did happen. All right. I think that's it. Sorry. Thank you.
Thank you so much, Steve.